So we're now going to look at two types of function and what their derivatives are. And the functions are linear and power law functions. So we'll start with linear. And a linear function is when y depends upon x. Not x squared, not the square root of x, not the logarithm of x or anything like that, just on x to the power of 1. And the general formula for such a linear relationship is that y equals mx plus c, m times x plus c, where m and c are constants. And if we plot such a relationship on a graph as x, y, we get a straight line, hence the term linear relationship. And the slope of the straight line is m. And the straight line intercepts the y-axis at c, which is where x equals 0. That's a y-axis. And we can see that from here, because when x is 0, y equals m times 0 plus c. So y is just c. And in the special case where c is constant, special case where c is 0, the straight line will go through the origin. And in that case, y will be strictly proportional to x, so that if we double x, we double y. And just to give a sort of practical example, if we look at cities of different sizes, different populations, put P, and count the number of doctors' surgeries, you sort of find something like that, and it's a straight line. So it's a linear relationship. But if we look at the petrol stations against the city size, we find something more like that. It bends over. It doesn't go up in a straight line. So this is linear, but this is not linear. We say it's sublinear because it, that the straight line would go there. It bends below the straight line. And why is that? Well, it seems to be that doctors' surgeries have a typical size, and people expect to have their doctor's surgery in their neighbourhood, within a certain reasonable distance. So doctor's surgeries cater for a typical population. And as the population of the city increases, then we just need more doctor's surgeries to cater for the new people. So it just keeps going up linearly. But with petrol stations, that's not the case. People don't demand that their petrol station is in their neighbourhood. They're driving around the city anyway, and so they can just fill up when they're out on a trip. And so that means that petrol stations can kind of cater to the whole city, and so they can increase in size. They can take advantage of the bigger number of potential customers and just have more pumps. So we find that the petrol stations get bigger in larger cities, and so we don't need as many of them proportionately as we do in smaller cities. So that's why it doesn't go up linearly, but it bends over. So there's a non-linear relationship, and that's a linear one. And at the moment, we're just interested in the properties of linear relationships. So we're interested in the derivative. If y equals mx plus c, what's dy by dx? Well, we said when we considered the derivative that it corresponds to the slope. It's the rate of change. And the definition of the slope is how much you go up for a given distance along. So in this case, this would be dx, the change in x, and that's the change in y. and dy divided by dx is the definition of the slope. So we can just go straight to the fact that because I said in this equation m is the slope, that dy by dx equals m. But I'd like to derive that in a couple of other ways just to help develop our intuition about these things. So firstly, we can do the same kind of calculation we did when we first looked at the idea of derivative, which is to say we're interested in the change in y as we go from x to x plus dx. So we increase x by an amount dx. What is the change in y? So we're taking y firstly at x plus dx. Well, when x is x plus dx, it will be m times x plus dx plus c. And then we subtract the value at x to find the change, the difference. So that's minus mx plus c. So that's a value at x. That's a value at x plus dx when we've changed x by dx, and we're interested in the change in y, how it depends upon the change in x. Well, we can simplify this. We've got mx plus m dx plus c minus mx minus c. And clearly we can cancel the c's, we can cancel the mx's, and we're just left with m dx. So we've got dy equals m dx, and then we can take the dx down, just treating this like a fraction. Dy by dx equals m. That in a nutshell is what we did in the first lecture when we were considering how we get a derivative. We took an x plus dx and an x, and we found the difference between them, though in that case we were looking at squares. And I now going to look at it a second way. Because this is a sort of technique or way of thinking about things that will become useful later on when we look at some of these mathematical historical theories. So we're interested in dy, the differential of y, the change in y. And that means we're interested in d of mx plus c, because y equals mx plus c. Well, this is a change, so when we've got two things added together, the change of the two things added together is just the sum of the changes in each one. So we can write this as d of mx plus d of c, which I can just write as dc. Well, c is a constant, so the change in c is 0. It's constant, so it doesn't change, so there's 0 change in c. And then here, m is also constant, so m doesn't contribute anything to the change here. The only change is due to change in x. X is the variable. So the difference in mx is just m times the difference in x, the change in x dx. So again, we've got dy by dx equals m. And the point of doing this is just to introduce you to this idea of working with differentials of expressions. And you know, we've seen a couple of rules here then about how we can apply this differential as an operator, we can think of it as, to this expression, so that when we add, when it's added inside, we just it's still almost as though it's just multiplying out the bracket. We can just apply it to the parts of the expression that are added together, and when it's multiplied again, we can just take the constant out to the front here, leaving us m dx. So there's a sort of couple of rules for dealing with differentials, and as I say, we will be using these ideas of differentials in some of the theories we will look at. So that's linear relationships. Now we'll move on to the next one. So I said the second type of function we'll consider is power laws. Power law. And a power law is when y is proportional to x to the n, where n is some number. And when we talked about exponents, we called this the exponent. We also called it the index, and we can also call it the power. So we say y is proportional to x to the power of n, to the power n. Well, we're interested in the derivatives then of power laws. Well, we've already seen one. When y equals x squared, we saw that dy by dx equals 2x. I hope you recall. And I'm just going to recap how we did that, how we found it. So we said if y equals x squared, then dy by dx is equal to the change in y as we go from x to x plus dx. So the change in y is the value of y at x plus dx. Well, y is x squared, so that will be just x plus dx squared. Take away the value at x, which is just y equals x squared. And then that's all divided by dx. Well, x plus dx we just need to multiply out the brackets. So that's x squared plus 2x dx plus dx squared. And then it's minus x squared, and that's all over dx. And then we can cancel here the x squareds, and the dx's cancel, that one we get rid of, and this, it cancels with one of these dx's, so we just are left with dx. So we get 2x plus dx, and dx is 0, so we get rid of that. So dy by dx equals 2x. That's just a recap of what we did in the first lecture, in a nutshell. Well, we can apply the same idea to y equals x cubed. So let's do that. Y equals x cubed. What's dy by dx going to be? Well, it is the difference in y at x plus dx and at x. So at x plus dx, we've got x plus dx cubed now, because we're looking at y equals x cubed, minus the value at x, which is just x cubed. And that's all over dx. Multiplying out this bracket, it's x cubed plus 3x squared dx plus 3x dx squared plus dx cubed, and then there's minus an x cubed at the end, and that's all over dx. And now we can start the cancelling again. So x cubed we get rid of, the dx will cancel with that, we'll cancel with one of those, and it will cancel with one of those, leaving us there dx squared. So this is equal to 3x squared plus 3x dx plus dx squared. Well, dx again is 0, so we get rid of that, and 0 here times 3x, 0 times anything is 0, so we get rid of that as well, and so we're just left with dy by dx equals 3x squared. And then we can do something like this for the general case. Where y equals x to the n, and I'll just go straight to the result. but we find that dy by dx equals nx to the power of n minus 1. We can see that that works for the examples we've considered. So if it's x squared, it's going to go to n. In this case, n is 2, so that's 2 times x to the n minus 1. 2 minus 1 is 1, and x to the 1 is just x. So x squared is 2x, and we also have just seen x cubed, which will go to n is 3 now, so that's 3 times x to the n minus 1. 3 minus 1 is 2, 3x squared. So that formula certainly works for the examples we've seen, and that is our general formula for a power law, how to differentiate it. And we can also just generalize it a little bit further. If we say y equals ax to the n as a power law, where a is a constant, then we just have the constant multiplier. So it's a n x to the n minus 1. So we can also see that our case of y equals mx plus c is a special case of the power law. The linear relationship is just a power law with a power of 1, an exponent of 1. So if, for example, we've got our y equals mx plus c, dy by dx equals, well, that's x to the 1. So this is using here a times n is 1. Use a dot for multiplication. M times 1, which is n, times x to the n minus 1. N is 1, so n minus 1 is 0. Plus, and well, if we want, we could consider this as c times x to the 0. X to the 0 is 1, remember, so c times x to the 1, 0 is c times 1, which is c. So this is c times x to the 0. So again, applying this rule, n is 0, so that's c times 0 times x to the 0 minus 1, which is x to the minus 1. And 0 times anything is 0, so we get rid of that. 1 times x to the 0 is 1, so that's just 1, so we get dy by dx equals m. So the linear relationship is a special case of the power law. And while we're on this, we might just note then about the antiderivative, so that if we said that if y equals ax to the n, then dy by dx equals an x to the n minus 1. We can also then say if y equals, let's put it, well, we'll forget the a just to, if y equals x to the n, we just forget the a just to simplify the maths a bit, then the integral of y dx, the antiderivative, is going to be, well, firstly, when we go in this direction, we go from n to n minus 1. So when we're going in reverse, from x to the n, if we integrate that, we'll get n plus 1. And we also would multiply by n. So if we differentiated this, we would get an n plus 1. But we haven't got an n plus 1 in front, so we need to divide by n plus 1. So if y equals x to the n, the integral of y dx equals 1 over n plus 1 times x to the power of n plus 1. So, for example, if y equals x squared, taking the integral y dx, of course I should add a c because we're dealing with indefinite integrals here, if y equals x squared, the integral of y dx, is going to be integrating x squared, applying this rule, it's going to be 1/3 x cubed. And if y equals 2x, the integral of 2x dx is going to equal, well, it's 2 times, that's x to the power of 1, so that will become an x squared, and it's also 1 over n plus 1 in front, so that's a 1 over 2 in front, so it's 2 times a half times x squared, which is just x squared. And of course that is what we found before, that x squared has the derivative of 2x, 2x has the antiderivative of x squared.